As I said in the very first lesson, we have a hard time with words in this field, and so you have to learn a new word this time, and the word is allotropy, A-L-L-O-T-R-O-P-Y. A lot of metals, in fact a lot of materials, are possessed with allotropy. That is to say, if you took a piece of quartz, or silicon dioxide, you find that that particular material, quartz, can exist in more than one form. It will always be chemically the same, but as you change the temperature on this piece of quartz, it'll change its crystal structure. And in fact, it'll change it 2 or 3 times. We should recognize allotropy very easily because we deal with the material, all of us do, that has a very low temperature allotropic transformation. But we never see it, or we don't normally see it. And that particular material is tin. Tin, which you generally see as a silvery, ductile material, has an allotropic transformation at 19 degrees C. That's just below room temperature. When it changes from this silvery, ductile material to a gray powder. And it changes to a gray powder because it changes crystal structure. And the new crystal that it moves into as you drop the temperature is so different in its density, in its volume, that when it changes from one crystal structure to the next crystal structure, it is unstable. It is incapable of hanging together as one piece. And so the crystals, as they form, just pulverize the material. So you would think that if you put a tin-coated can in the refrigerator, you'd certainly take it out and see gray tin. But you don't, because it requires nucleation. And at this low temperature, the nucleation is very, very slow to occur, and the growth of the material is very slow to occur at around room temperature. So if you want to see gray tin, you generally have to go to a museum. Or perhaps you have an old pewter, if you have an antique pewter beer mug sitting around, it's black and has a brittle coating on the surface of it, you can be pretty sure that that's an allotropic form of tin. Well, iron has 4 allotropic forms, and those 4 forms are exhibited for us as a function of temperature and range from a room temperature, or actually from absolute 0, up to about 1400 degrees as a body-centered cubic structure. Now we'll look at a picture of that structure in a moment, but let's just say it's a certain crystal structure. If we heat the material up to 1400 degrees, it stays body-centered cubic, but it changes a property, a significant property. That is, below 1400 degrees, it's going to be magnetic. And at 1400 degrees, we reach something called a Curie temperature, and it changes to a non-magnetic material. So something is different about it. So most people say it's one of the allotropic forms of iron. This particular material, beta iron, exists up to approximately, and by the way, the correct numbers are in your book, but approximately 1700 degrees, when it changes from a body-centered cubic material to a face-centered cubic material. And we have a volume inconsistency here, just as we had in the tin, except it is not as severe, and the material doesn't fall apart, stays in one piece, but there's a tremendous volume change that occurs. It stays as a face-centered cubic form until it gets up around 2700 degrees Fahrenheit, and at that time it turns back to body-centered cubic. It's no longer magnetic up at that temperature, and it's a different crystal structure. And if we went up there, we would find that there was a volume change up there as well. I thought it might be interesting this morning to look at this transformation, because you see evidence of it if you heat a piece of steel that is approximately the eutectoidal composition up to the face-centered cubic range. Now that temperature is 1333 degrees Fahrenheit. So if I could take this piece of wire, which is suspended between 2 electrical terminals, if I could heat that up, which I will do by passing an electric current through it, I could make it sail up to a temperature of, say, 1300 degrees. When it got to that particular temperature, what would happen is that the wire, which has been expanding, all of a sudden will want to contract. And that says that in this face-centered cubic structure, we will occupy less volume, and if the lattice parameter stays approximately the same, the wire which has been expanded will tend to contract. Now on heating, that's a little difficult to see, but on cooling, it is relatively easy to see. So if you were to watch the keys now that are hung on the wire to see their progress going up and down, then you will see that you can observe the evidence of the allotropic transformation. So I'll just plug it into the current, and the wire begins to heat up, and it goes down, 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 down. Hesitates, goes back up slightly. That's a little difficult to see. But then when we cool it off, it goes up and down and up. Let's try it once more. Goes down, 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 down. Takes a little while to heat up. The air's cooling the wire off. And now we go up and down and up. You see that? Well, that is evidence of allotropic transformation of iron. Now, we could show that in a lot of materials, and we find that we may have played a little bit of a trick on ourselves. Because, for instance, if I took a material like this material, the little black bar you see in my hand is a sheet of alloy, a special alloy. Now, yesterday, or in a previous lesson, we plastically deformed the material, and we know what happens if we plastically deform the material, right? So, did it get harder or did it get softer? Got harder. Well, the fact of the matter is it didn't. Not this time. Because this time, what happened is the deformation induced a transformation in the material. And this particular material remembers what it ought to be like. So if we put enough thermal energy in it, like if we would dip it in a cup of hot coffee, it's straightened back out again. I don't have a cup of hot coffee. That's a little messy. But if we just heat it up with a match, we find out that if you look closely at it now, it'll just straighten right back out. Okay? How'd you like to have the fenders on your car made like that? Well, this particular material is something that's called a trip-type material. It's transformation induced by plasticity. That is, I'm going to cause the material to change to another form, to another, actually something called a martensitic form, just by bending it. So what we want to find out now is what's really going on when we go through these allotropic transformations. So one of the first things that we should do is to look at what these structures look like that are the face-centered cubic structures and the body-centered cubic structures. And we find here that we have what exists as in iron as a room temperature structure. We presume that we're looking at the atoms of the material now, and they're situated at the corners of a little cube, and in the very center of that cube is another atom. And so we just say it's body-centered cubic. The fact of the matter is that every one of those corner atoms is shared by 3 other little cells that would be tight against it, and 4 cells that would sit on top of that cell. And so that corner atom is really contributing only 1/8 of an atom to that unit cell. And since there are 8 corners, that means we have 1 atom contributed by the corners and 1 atom contributed by the center one. So there are 2 atoms per unit cell in the body-centered cubic structure. If you look at the face-centered cubic structure, or the structure that's going to exist at a higher temperature, we see a structure that looks like the next one, which is a face-centered cubic structure now having 1 at every corner, atom at every corner, an atom at every face. Every face. There's 6 faces, and so we have 6 face atoms. The corner atoms are still going to contribute 1/8 of an atom per unit cell, but the face atoms are shared by this unit cell and the unit cell immediately adjacent to it, so it contributes 1/2. And since there are 6 faces, that means we have 3 atoms contributed as face atoms to the unit cell, or we have a total of 4 atoms per unit cell in this particular structure and only 2 atoms per unit cell in the body-centered cubic structure. So you see where if the lattice parameters stay the same, it doesn't stay exactly the same in that transformation, we would expect to get a rather big volume change. Now, we have to remember that the wire that I tried to show you this with is sort of short, and that we make products that are very long. If you were to go into a steel mill where they were rolling railroad rails, for instance, you'd find that if they rolled a railroad rail out next to you and you were standing there looking at this red-hot rail, if you could do that, and it was butted up against the wall on one end and you were standing at the other end, all of a sudden this thing may change in length by as much as 2 feet. They just go boom, and it's going to be that much longer. So it gives us a problem if we want to cool the metal fast, if we want to do something to heat treat it.
Allotropic transformation is a change in crystal structure due to temperature. In some materials, this change can also be caused by bending. Iron has 4 allotropic forms, in temperatures ranging from absolute 0 to 1400 degrees Fahrenheit. Below 1400 degrees Fahrenheit, iron is magnetic. Above this temperature, iron loses its magnetic behavior, indicating that a change has taken place. At approximately 1300 degrees Fahrenheit, iron changes its structure from body-centered cubic to face-centered cubic. In a body-centered structure, each corner contains an atom, and there is 1 atom in the center. However, face-centered cubic crystals contain an atom at every corner, plus an atom at the center of every face.
Now what we're going to do at this time is look at a transparency. I'll look at the iron-carbon equilibrium diagram just briefly. We'll come back to this many times, but we want to look at this particular diagram to talk about the allotropic transformation. Now actually, what we have in this particular structure, in this particular diagram, is the carbon content shown going from 0 to 6.66%. That actually happens to be what Fe3C is. And you notice we have shown steel as existing from 0 up to 2% carbon. Now you can have a new definition for steel, because you can say that steel is a material which can always be converted to this high temperature phase as one phase. Notice that if we're beyond 2% and we heat the material up, we'll always go into a 2-phase region. But we can, in a solid state, heat any piece of steel up high enough to make it into this material that's referenced as gamma, and for which we have a name, and we call it austenite.